In our last couple of lessons, we talked about how to answer or approach questions regarding sample means. First, we did one sample mean, and then we did two sample means where the populations were dependent and the populations were independent. Now we're going to shift gears and look at what happens if we're trying to make an inference about a percent of the population or a population proportion by using a sample proportion. Our objectives for this section are going to be to describe the sampling distribution of a sample proportion and compute the probabilities of a sample proportion. Just like in the sampling process for the mean, each time I take a random sample and I measure a proportion with a characteristic, that sample proportion will change between samples. So there is a distribution of the sampling process for the sample proportion. We want to discuss what we mean by that sampling distribution. First, we need to talk about the point estimate that we get for a population proportion. That point estimate will be called the sample proportion. The sample proportion, denoted by p hat, is an estimate of the population proportion, p, and it's given by the number of individuals in the sample with a specified characteristic divided by the total number of people in the sample. So it's the number with the characteristic divided by the total number asked, or total number measured. For example, in a Quinnipiac University poll conducted in May 2008, 1,745 registered voters were asked whether they approved of George Bush handling the economy or didn't approve. 349 responded yes, they approved to his handling of the economy. A point estimate then of the proportion of registered voters who approved of the way he handled the economy would have been the number of people with the characteristic we were interested in, which would be 349, divided by the total number of voters we asked would be 1,745. So the point estimate is 349 over 1,745, which is 0.2, or 20% approved of his handling of the economy. The second example would be, according to Time, they conducted a poll in June of 2008. 42% of registered voters believe that gay and lesbian couples should be allowed to marry. Describe the sampling distribution of the sample proportion for samples of size n equals 10, 50, and 100. Well, let's look at what happens if we run some different simulations to see what the distribution of the sampling process would look like. With samples of size 10, we see something where it's grouped around the middle of it, around 40%. Gives me a mean of 0.426 and a standard deviation of 0.16. If I use samples of size 50, I get a mean of 0.426. My standard deviation has gone down now, though, because I'm using more people in my proportion, or in each sample. The variability between samples should decrease, just like it did with the mean. Now, if I use 100 in each sample, I again get a mean of 0.42 and a standard deviation of 0.047. Using a higher sample size gives me a better estimate of the mean, and I get, or estimate of the proportion, and I get a much lower standard deviation. Notice that the curve here is roughly bell-shaped as well. So the key things to remember is just going to be exactly the same types of relationships that we saw with the mean. As the sample size increases, the shape of the sampling distribution does become approximately normal. It is centered around the true proportion. So the more samples we take, the better estimate we'll get of the true population proportion. The spread of that process will be closer and closer to the sample proportion, or to some relationship between the proportion deviation, and that as n increases, that standard deviation does decrease. If we go back and we look, when n equals 10, the standard deviation was 0.16. When n equals 50, the standard deviation was 0.072. And at 100, I had a standard deviation of 0.047. So as n increased, the standard deviation decreased. That all leads us to the following information. For a simple random sample of size n with a population proportion p, the shape of the sampling distribution of p hat is approximately normal, provided that n times p times 1 minus p is greater than or equal to 10. The mean of the sampling distribution of p hat will be the true population proportion of p, and the standard deviation of the sampling distribution of p hat, denoted by sigma sub p hat, will be the square root of p times 1 minus p over n. Just as before, we will get a mean of the sampling distribution. We will get a standard deviation of the sampling distribution. Just as before, the mean of the sampling distribution should come up to be the parameter at which we're estimating, in this case, the population proportion. The standard deviation calculation does look much different than what we had before. The reason for the difference here is because we have a change from mean to proportion. By using proportions, we get a different standard deviation formula. Okay. So the model does require that the sampling values are independent of each other. In other words, when I ask people the question, I will assume that the respondents are independent of each other. We can verify this if we have a finite population. We can verify that this assumption is no more than 5% of the population. So we want the sample size to be small compared to the overall population size, as we did with the mean. And we do need to have that n times p times 1 minus p is greater than or equal to 10 for this to be normal. However, regardless of if that is true, the standard deviation will still be p times 1 minus p over n. Again, this restriction is what gives me the normality of the distribution. Okay, so going back to our example of 42% of registered voters believe that gay and lesbian couples should be allowed to marry. Again, remember, this book was done several years ago. This percentage has changed dramatically since then. Suppose that we obtain a simple random sample of 50 voters to determine which voters believe that gay and lesbian couples should be allowed to marry. Let's look at the sampling distribution then of that sample proportion. Well, we would expect that the overall mean of that distribution would be the proportion of 0.42. 50 is certainly less than 5% of all registered voters, so we know we've matched that. 50 times 0.42 times 0.48 is bigger than or equal to 10. So I know that this distribution will be approximately normal now. And the standard deviation is going to be the square root of 0.42 times 1 minus 0.42 over 50, which is 0.0698. Notice when we did our sampling, or our simulation process, where we ran a number, I think it was 300 of these samples, we did come up with something that was close to that value. So now let's use the fact that this distribution is normal and calculate probabilities from that normal distribution. So let's do a couple of examples. According to the Centers for Disease Control and Prevention, 18.8% of school-aged children aged 6 to 11 were overweight in 2004. In a random sample of 90 school-aged children aged 6 to 11, what is the probability that at least 19% are overweight? And what's the probability, or given that we end up with a sample where 24 of the 90 are overweight, what might we conclude? So 90 is certainly less than 5% of the population. 90 times 0.188 times 1 minus 0.188 is greater than 10. So again, we know that this would be approximately normal now, and they're independent. The p-hat distribution will have a mean that's approximately 0.188, and the standard deviation will be the square root of 0.188 times 1 minus 0.188 over 90, which is 0.0412. So I want to know the probability of being greater than 19%, or at least 19%, means I'm going to look at a z-score. Again, we have a mean and we have a standard deviation. So we can calculate our z-score using that information. Remember, z is x bar minus mu over sigma. In this case, it's going to be the observed proportion, p hat, minus p over sigma sub p. So we end up with z equals p hat minus p over sigma sub p. P hat is the sample proportion, which is the mean for our observed data, and p is the overall population proportion, and sigma sub p is the standard deviation of that sampling process. So we took 0.19 minus 0.188 over 0.0412, which gives me 0.0485. Rounding that to 2 decimal places gives me 0.05. I now want the probability that z is bigger than 0.05, which is the same thing as, remember, 1 minus the probability that z is less than 0.05, which is where the 1 minus 0.5199 came from. So we end up with an overall probability that at least 19% are overweight of 0.4801. So there's a 48% chance that at least 19% of the population is overweight. So now let's move on to our next one. We know that the distribution of the sampling process for the proportion has a mean of 0.188 and a standard deviation of 0.0412. Now let's suppose that we actually had a sample of 24 overweight children out of 90. that would tell me that the sample proportion is 24 over 90, which is 0.2667. That gives me a z-score of 1.91 standard deviations above the mean. So in other words, we figured out the sample proportion minus the mean over the proportion standard deviation of 0.0412 gives me my z-score. If I want to know what the probability is of observing 24 or more overweight children, that would be the same thing as observing the probability that z is bigger than 1.91, which is 0.028. So we would only expect about 3 samples in 100 to have a sample proportion of 26.67% or more. This is an unusual sample if the true proportion is 0.188. One thing to note here is notice that when we went to proportions, the sample sizes are large enough that we are now using the z-table and no longer using the t-table. So in sample means, we've used the t-table for all of our calculations. With sample proportions, we will always use the z-table. So as a conclusion, remember that the sampling distribution for a population proportion will have the same mean as a population proportion I'm trying to estimate, and the standard deviation will be p times 1 minus p over n, and take the square root of that expression. So sigma sub p hat is the square root of p times 1 minus p over n. This concludes our discussion of section 8.1.